All right, let's do it. The acid-base equilibrium. So in this case, acid-base equilibrium. So acid-base equilibrium. Now, if you remember from like analytical chemistry, so you have HA plus, let's say, water, H2O, and then so HA has been being acid, and then water is working as a base, and it's in equilibrium. So it's going to make hydronium ion, H3O plus conjugate base, A minus, right? And both, they're all aqueous, so we don't have to, well, let's just be polite, chemically polite. So I'm just going to put, aqueous, right? So, equilibrium constant in this case, if you want to write an equilibrium constant, K is equal to H3O plus, and let's just, and then activity of that times, activity of A minus divided by activity of HA, and, times activity of H2O. Okay, that's reasonable. That's equilibrium constant expression. Remember, H2O is not aqueous. Sorry about that. It's actually H2O is a liquid phase. When you have liquid phase, the activity of a liquid itself is 1. So it turns out this is what we call H3O plus times activity of a conjugate base divided by H and HA, activity of the acid. Turns out that this expression right here is what we call acid-base equilibrium constant, so Ka. So keep that in mind. So now this one, of course, this is equal to roughly about the same as the concentration. So it's going to be, H3O for dilute system. You can assume that activity is about the same as a the molar concentration, so concentration of acid. So that's what we have as a acid equilibrium constant. So keep that in mind. Now that said, right? So when you look at this, by the way, that's what you are told in analytical chemistry. This was the acid equilibrium constant. Of course, when you look at it, the unit on each one is a molar concentration. So if you have molar concentration, all of these, and then, this cancels out with this, but then you have this, which doesn't make sense because equilibrium constant should have no unit, right? No units. But, but they don't cancel out. So what's happening is the real question. The units don't cancel out. Turns out that actually, you are using the numerical value for the concentration, molar concentration, but in reality, it's an activity. And activity doesn't carry units. So activity on each of these terms are unitless. So turns out the activity doesn't have a unit. So therefore, equilibrium constant doesn't have a unit because they don't need to cancel the units. So keep that in mind. So again, it's a no unit. So keep that in mind, right? So because it's a no units, right? So no units or no unit, right? Because activity doesn't carry units, right? So keep that in mind. Just molar concentration just happens to be for the dilute system. Numerically, they are about the same as activity. And that's why we use that for molar concentration. But in reality, activity is based on the vapor pressure. So keep that in mind. So, but going back, also what you have learned in acid-base chemistry, in analytical chemistry, pKa. Remember, P is a function of some P is a function of the value that goes into the function, right? So f of x, right? So in this case, pKa is the function that actually puts minus log of whatever, in this case, Ka. right? So log of base 10. So keep that in mind. So so that's what the P function is. So pKa, you can call that as minus log of Ka. It's a log base 10. So keep that in mind. Now, but what is Ka? Well, what is pKa? In a physical sense, what is what is pKa, right? What does this tell us, right? Remember that the for pKa is where conjugate base and acid concentration, right? Conjugate base and acid concentration are uh, existing the equal amount. So equally, I'll just call it equally. All right. So keep that in mind. Of course, you know that from the biochem, but so where the pKa value is, just so keep that in mind. Kb, by the way, just just going over some terms. Kb is equal to, well, activity of the activity of B base with acid, or I mean acid, but times activity of let's say activity of B, and then activity of OH. When so keep that in mind. Well, I mean, I use B, so let's see. B plus the B plus oh, let's call that B minus plus H2O. So you have base, and then you have water, and now water works as an acid, so provides protons, so BH plus OH minus. So keep that in mind. So this is OH minus. So keep that in mind. Now, of course, this one is equal to roughly about the same as a concentration of BH times OH minus divided by activity of B. So keep the base. So keep that in mind. Just to remind you, Kw is equal to Ka times Kb, which is equal to 10 to the minus 14. So just keep that in mind. Now, that said, going back, buffers. So now, just a review for buffers. Buffers is, you can construct buffer by adding weak acid, and its conjugate base. So conjugate base, right? So, and then you get the buffer, right? So let's say you have HA and A minus pair, right? Or you can do you can do a something like maybe B and B and BH pair, right? Or you can call a B and BH pair as well. You can call that something like an example would be like, this one, I'll just give you an example, something like NH3 and like NH4 plus. Well, this technically speaking, it's not a great example, but something like this. So keep that in mind. I'm just gonna well, because it's not a great example. Perhaps tris buffer or something might be a better example. Anyways, and then we'll probably know why later. Anyways, so here we go. pH, right, is equal to pKa minus log of activity of HA times activity of the conjugate base, right, which is about the same as concentration. So pKa minus log of concentration of in this case HA over A minus. Again, this is all review from analytical chemistry, but or sometimes you see this as a these two are being flipped. So you may have pKa plus log of now conjugate base is on the in the numerator, and then HA. So keep that in mind. You might see in one of these two equations. What's important? Now, this is equal to pH. So pH of the buffer is determined by its pKa, and from the deviation from the pKa based on the concentration you have for each species. So keep that in mind. So now, going back to the question earlier, what is pKa? pKa at pH, pKa, well, at that particular pH, where the pKa and pH is, then, well, pH is equal to pKa, where conjugate base and the acid concentration are the same, because if this concentration and if this concentration are the same, they will cancel out. If they cancel out, it's going to be 1. Log base 10 of 1 is equal to what? 0. Therefore, pH is going to be pKa when these two are the same in the concentration. Let me write that down. Underneath here, I'm going to just use this space right here, but underneath here, write this down, right? At HA, right, is equal to A minus concentration-wise. Then, right, at that point, all right, the log of HA over A minus would be, well, this part right here is equal to 1. So log of base 10 of 1 is equal to 0. So at that point, pH is equal to pKa. So keep that in mind. This goes underneath here. Right now, going back. So let's continue. So I'll just give you an example because you may have to make a buffer. So let's say, find the pH of a solution. pH of a solution prepared from, let's say, dissolving 12.43 grams of tris. A molecular weight or formula weight is equal to 121.14, right? Grams per mole, right? And plus 4.67 grams of tris HCl. In this case, molecular weight is like 157.60 grams or so, grams per mole, right? In 1.00 liter water. So what would be the pH, right? In this case, a fine, so I don't need the question mark here, water, right? So, and you can assume, right? Assume the activity of tris is about the same as activity of tris HCl. So keep that in mind. And of course, a couple more information. You can always look up the info. pKa of tris. pKa of tris is equal to roughly about 8.07. So let's go from there, right? So then, well, in this case, it's like, in this case, B, and then you have BH, tris H, HCl. So, in this case, well, you have 12.43 grams per liter. And of course, molecular weight or formula weight is 12.14 grams per mole. So in this case, grams cancels out. So you can get 0.1026 molar concentration also. BH is equal to, I'm just going to go this side, all right, 4.67 grams per liter divided by 157.60 grams per mole. So then is equal to, and then 0.0296 molar. So in that case, let's just plug and check. pH is equal to, and then, pKa plus log of, in this case, you can just do 0.102. You can put 6 divided by 0.0296. And of course, pKa is this value, so it's equal to 8.61. Done. So that's the end of the setup. So simple, straightforward. Just to make buffer based on the known mass, and then if you actually measure the 12.43 grams of tris and then 4.67 of tris HCl, mix it up together in one, so just weigh it and dissolve into 1 liter, and then you end up getting this pH. Boom, done. Of course, you may depending on temperature, it might shift, because again, pH and equilibrium is a temperature dependent value. So if the temperature is not, so depending on where the temperature is, this may come out at slightly different pH. But now you know that this is how to set up the buffer. Of course, you may want like a buffer pH at like 7.00. Questions: how do we do that? Of course, once you have that, you can start adding like HCl, 3 molar HCl or something, and you can just start adjusting your pH. And that's typically how the buffer is made, anyways. But I'll give you some example. So let's say another example. So let's say how many, all right? So how many milliliter of 0.500 molar NaOH should be added to 10.0 grams of tris HCl, right? To give a pH is equal to 7.60, right? In a final volume of 250 milliliter. So again, this is like a buffer preparation. So you want to make a final volume of 250 milliliter and at final pH at 7.60. So, and then starting with 10.0 grams of tris HCl, right? Of course, you can change this. I mean, like typically, if I'm making a buffer myself, I would use like maybe 3 molar NaOH or something. But anyways, so just to give you the idea, again, in this case, you have tris. So BH plus is the tris. So well, and well, you can just call it in BH plus, and then this is the tris part, and then Cl minus. So tris Cl minus, all right? Tris H, right? Cl, and then going into B minus in this case, or B. Wait, you can call that B, all right? Plus H plus plus Cl minus, right? So, but in this case, you have pKa, and then pKa for this is equal to 8.07. All right. Now, and then so that's the system. And then of course you have to make an ice table. In this case, you have tris HCl, right, is equal to BH plus, right? And then so you can call that BH plus plus OH minus going into B, right? Plus H2O, but anyways, and then so initial, and then I'm gonna call final. I mean, you can do the change too, but initial you have. I'll just give you the value. So 10 grams, by the way, 10.0 grams will give, you'll have how many you can just calculate 0.0635. So I'm just going to write that 0.0635 moles, right? And you don't know how many moles of OH you need, but change would be 0.0635 minus X, right? And then, of course, at the end, you don't have OH because it's reacted, and then you form X amount of the tris. So, and once you have that, then, once you have the ice table, I mean, you have the, ice, this is at equilibrium, but the final, I just call that. So pH in this case is equal to pKa plus the log of, in this case, I'll just use moles of B and then moles of BH. The reason why you can do it this way is because you don't need the volume per se, because final volume is the same. So moles per 250 milliliter on both numerator and denominator, so they'll cancel out. So I just use moles, because technically you could do per 0.25, and you could do that on both, but then equation just gets too messy. So I'll just use the number of moles, because both of these, numerator and denominator, we both have the 0.25 anyways. So after that, this is equal to 8.07 plus log of X divided by 0.0635 minus X. Boom. So once you have that, and then, well, is equal to, pH is equal to, final pH is 7.60. So is equal to the whole thing, right? This whole thing is equal to 7.60. So if you have that, then you just solve for X. Boom, done, right? So easy peasy. How do we do that? Let me just erase this part. So now, 8.07, 7.60. So you take a difference. So in this case, I'll just do the algebra, 0.47. Take this on the other side of the equation, all right? 0.47 minus of that is equal to log of, and then you just still have the same X over 0.0635 minus X. Boom, easy peasy, right? And then how do we do this? This is log base 10. So you just take, you take a 10 to the minus 0.47. Again, this is a little bit of algebra, but, take, 10 to the power on both sides. So log base 10 to the 10 to the power. It's going to, well, I mean, I can just write that for you. I mean, I guess, you can just do the log of, or you can just 10 to the, sorry about that. You're doing 10 to the log base 10, right? And then you have that X over 0.0635 minus X, right? Maybe it's been a while, so it's log base 10. So this turns into, well, boom. Well, this will just make that X minus 0.0635 minus X. You just have to do a lot of these, math algebra stuff to just, get into the pace. But then 10 to the this, and you can just do that, and you can just calculate it as something like 0.339 or so, I think, is equal to, and then, X over 0.0635 minus X. So after that, you solve for X, and boom, you're done. I'll give you the final answer. In this case, 0.0161 mole. By the way, that's because you dealt with number of moles, right? So this is a rookie mistake if you just leave that, because remember, in this case, you want to have a final, oh shoot, I erased that, but you want to have a final concentration or of the you want to have a final volume, but also you are using 0.5 molar NaOH. So in this case, how many moles of the NaOH do you need? In this case, you got this many moles, so it's going to be 0.0161 mole divided by 0.500 moles, so is equal to, and then, well, in fact, I'm just going to go like that, is equal to I'm just going to go like this, a little bit easier to see. In fact, I'm going to erase this part right here, is equal to, and then it's going to be 32.2 milliliter. So boom, done. So this is the volume of NaOH you will need. So after that, so to get the to and then well, this is the how many milliliter equivalent you need to achieve 7.60. After that, you just dilute. So basically, so you have your volumetric flask. In this case, this is a 2, so you got 32.2 milliliter of NaOH, right? And then and then so this will give you, this will end result is 7.60 pH. Once you have that, and then you just fill it up to all the way to 250 milliliter, boom. So you just fill up with H2O, because water dilution will not change your pH. Once pH is set to 7.60, it's going to be 7.60 no matter how much water you add in. So keep that in mind. All right, so easy peasy, right? So right, that's pretty good for now. So I'm gonna stop that video so that you can rest a little bit. All right, then I will see you in the next video.